first, I just want us to think about if there's an electric current and I'm applying it to this solution, what that means is that the parts of that solution are going to undergo electrolysis. And that means that we're breaking apart this compound into its elements. Okay, so I have NaI aqueous, and it's going to break down into Na solid. And okay, so with this, we have two different half reactions that are happening. So we have our sodium going from a +1 to 0 oxidation number, and our iodine is going from -1 oxidation number to 0. Okay, so with my sodium going from +1 to 0, it has obviously gained electrons. It's being reduced. And the iodine is going from -1 to 0, so it's losing electrons. So it is being oxidized. Okay, so there are possibilities for what the anode and the cathode could be, and this is just one set of them. So we will look at them separately. So first, one thing that could happen at the cathode, which is reduction, is my Na plus ion could be accepting an electron and becoming Na solid. And one possibility that's happening at the anode is that I have I minus, and it is forming I2 gas, and it is giving off an electron, losing an electron. Now, when I balance this, I do have 2's in front of my I and my electrons. Okay, so for this iodine, my E reduction is 0.53 volts. And for the cathode, the Na plus is, and I'm going to keep this as a reduction, negative 2.71 volts. So when we're trying to decide which thing is going to occur at the anode and the cathode, if this was molten, this would be it. But because it's happening in solution, that means that water is present. And when it undergoes electrolysis, our water will form hydrogen gas and oxygen gas. I need to think about that could happen at those electrodes as well. And there will be like a competition between the iodine at the oxidation end and the sodium at the reduction end with the water, because water can be oxidized and reduced. Okay, so when I'm looking at these reactions, when I'm thinking about hydrogen in this case is going from a +1 to 0. So that means it's gaining electrons. So reduction is when I'm making hydrogen. And then oxygen is going from -2 to 0, which means it's losing electrons, or it's being, oxidized. So our oxygen is going from -2 to 0, so it's losing electrons, oxidation. So when I look at my reduction potentials for that, which one is showing me oxidation and which one is showing reductions? That's what I have to figure out up here at the top. So when I have hydrogen being formed, that is reduction. So this is my other possible reduction. That's happening at the cathode. So it could be, I'm going to write or, we have 2 H2O plus 2 electrons is making 2 OH minus plus H2. I don't want to go into the hydrolysis and why we have these other species that are present. There's another video for that if you're wondering, why don't we just get hydrogen? Okay, and then the reaction that is for oxidation is making this oxygen gas. And when I look, the oxygen gas is in this equation. Now it's currently written as a reduction though, so I would want to reverse the equation. 2 H2O is making 4H plus plus O2 gas plus 4 electrons. Okay, so my reduction potential for the one that is producing oxygen, which is my oxidation, is 1.229 volts. And down here, the one that is making hydrogen, sorry, we got that confused earlier, is 0.83 volts, and this one's negative. All right, and when I'm trying to decide which one's going to occur, when I'm looking at the cathode end, it's the same reasoning we've always used. Whichever one has a higher reduction potential, that's the one that's going to be reduced. So this is the actual reduction half reaction that's occurring. So we know this one is not. And it makes sense because I would need nearly 3 volts of energy to make this one go because it's so far away from being at 0 on that part. Then when I look at the oxidation choices, I always want to choose the one that's closest to 0. Because that one will take the least amount of energy to run the cell. Okay, so it's always going to choose the one that I'm going to need the least energy to do. So that one is this equation here. So this is going to be my oxidation half reaction, and this one for the water is going to be my reduction half reaction. So let's just clean that up real quick and get rid of the ones that are not actually occurring. All right, so now it says to write the overall reaction. My electrons agree, so I don't need to multiply anything through, so I'm literally just going to add them together. Anything that's on both sides will cancel out, and that is the only thing that will cancel. So 2I minus aqueous plus 2H2O liquid is going to make I2 gas plus 2OH minus aqueous plus H2 gas. Then it's asking for the minimum voltage required. Again, we have to apply energy to this because it is an electrolytic cell. And so I'm wondering how much do I need to add to make that happen? So I'm going to calculate this just like I've always done. So E of the cell is my cathode minus the anode. My cathode value was negative 0.83 volts minus the anode 0.53 volts. And my value when I add them together is negative 1.36 volts. We expect this to be negative because it is not spontaneous, not thermodynamically favored is the terminology they like more now. So we expect a negative Ecell. Okay, so in order for this to occur, I have to give the reaction at least this much energy. So I need 1.36 volts to run, or to drive, I'll say, the process in the non-thermodynamically favored direction. All right, awesome. Hope that helps. Have a wonderful day.